Hi there. Welcome to Math Physics Academy. This week I am talking about rethinking teaching abstract algebra. I was torn between topics this week with my attention split between 2 to 3 level 1 courses I'd like to construct. Of course, these are not fully developed yet, so I ask the viewer or listener to adjust their expectations accordingly. As with my previous few videos thus far, this video presentation likely appeals primarily to other educators. The courses I have in mind are linear algebra and abstract algebra, and here I will focus primarily on abstract algebra. I managed to struggle more than necessary with this course, even with excellent help from friends and professors. I would not claim my struggles came from a poor structuring of the course. Nevertheless, the approach currently taken is often rather abstract. This is not a bad thing per se. However, as you might guess, I imagine a different approach. One final, possibly redundant disclaimer: this is still a half-baked idea and is filled with personal opinions. Many of the people I've previously shared this idea with, all of whom have a better grasp of and more skill in the subjects than I, tend to disagree that the approach I'm presenting here is better than the various approaches one may find in, for example, Dummett and Foote or Jacobson, or many of the other textbooks on abstract algebra. Additionally, many if not all suggested alternative approaches, most of which I will not mention, in part because I cannot do them justice. Lastly, I have not done an extensive search on whether or not others have investigated this approach, so I cannot attest to the originality of this approach at the time of writing, but I will update if need be. The approach does request the prerequisite of a semester or two of linear algebra, as it depends on relaxing the structure of a vector space. Since initially conceiving of the idea, I might also propose restructuring of a linear algebra course. See, for example, my very first video on the Introduction to Math Physics Academy. In my idealized situation, a full year-long course would cover linear algebra and abstract algebra in a thoughtful way. See the disclaimer. In this direction, I will sketch one of the approaches a colleague of mine offered. The student would first learn about groups through a simplified study of Galois groups. It would then make sense to define K vector spaces V as abelian groups under addition equipped with a group action by the field K. I prefer this approach to introducing vector spaces as opposed to the approach I and many other, at least US-based, students are taught, that of introducing 8 axioms that define a vector space. Again, see the disclaimer. At this time, the student should be satisfied with a group-based definition of a field, possibly avoiding rings initially. Introducing the role of groups in Galois theory, the definitions of a group and a group action, and finally the definition of vector spaces as groups acted on by fields, not only contextualizes groups but also sets the stage for the later reveal of rings and modules. Much of what we encounter in an abstract algebra course and a linear algebra course is interconnected, and of course these algebraic structures pop up all over the place in the undergraduate curriculum. The order of linear algebra first, followed by abstract algebra is standard, and in general many students will not take linear algebra until their second semester in their second year, or later. A consequence of this pacing is the student does not see abstract algebra until their third year. Many students in this situation are disadvantaged, whether we like to admit to that or not. So, let us return to this approximately year-long course in algebra, beginning with a study of linear algebra followed by what we call abstract algebra. In linear algebra, we would introduce students to groups and vector spaces as laid out in the Introduction to Math Physics Academy video presentation. From there, we will primarily leave the study of groups for later and focus on vector spaces and more or less the typical material found in such a course. Perhaps there could be mention of Galois groups from a bird's eye point of view, but as many of us know, it probably does not make sense to try to do too much here until after the students develop familiarity and comfort with algebra. Upon reaching a satisfactory transition point from linear to abstract algebra, we dive into the deep end. Return to the definition of a vector space we provided to the students on the first day of linear algebra. A vector space is an abelian group, along with a group action, by either the real or the complex numbers. Now, K is not merely a group, but a field. In other words, we have a notion of division, and further, everything commutes. I propose we perturb this structure to reveal other algebraic structures. Hit the piñata and let the candy fall. Many of the students may not know what candy lies inside, what it tastes like, whether or not they like that candy, and so on. I will attempt to be more specific. Perhaps a definition of a field should be introduced prior to this point or concurrently in terms of groups. A field K may be viewed as an abelian group under addition and an abelian group under multiplication, all in one structure. We are hand-waving a little here. Until now, we swept multiplicative inverses and division under the rug, largely because these are somewhat delicate notions. We might begin with posing students with the question, what if we have the same structure of a vector space, but take away our ability to commute elements of K, or take away our ability to divide by elements of K? What becomes of K and what becomes of V? We spent all this time not worrying about things like commutativity or division in K. Now we are peeling away the structure just a wee bit. First, let's focus on what happens with K. We may still view K as an abelian group under its addition operation, but now we are proposing taking away multiplicative inverses as well as commutativity of the multiplication operation. Let's hit the piñata at the commutative point. We have something called a division ring. Let's next hit the piñata at its division point. Now we just have a ring. A ring R is a set with two binary operations, addition and a multiplication, satisfying the following properties. R with addition is an abelian group, multiplication is associative, and we have some notion of distributive laws for the ring R. If multiplication is commutative, we call the ring commutative. If multiplication has an identity, we say that the ring R has identity or contains a 1. Now, rings are kind of weird, so we should provide some examples. The integers z with familiar addition and multiplication forms a commutative ring with identity. The quaternions, along with component-wise addition and distributive multiplication, which we are omitting here, form a non-commutative ring with identity. Polynomials with coefficients in a commutative ring with identity form a commutative ring with identity. We denote it with R of x, and as with the quaternions, addition is component-wise, multiplication is distributive. We're omitting definitions here for brevity. Lastly, we have the n by n matrices with entries from an arbitrary ring R. These form a non-commutative ring. We'll write m sub n of R for n greater than or equal to 2. If R has an identity, so does the matrix ring. So we've peeled back a field K into a ring R. What if our vector space's group action was by a ring R instead of a field K? Well, of course, we'll need another new term. A crucial question could be, do we lose our notion of linearity? What kinds of things can be multiplied but not divided? What kinds of multiplicative things cannot be commuted? The second and third questions can likely be answered by at least one student, although I imagine more could. The first question seems more subtle to me, but I am sure in any real-world execution of this idea, I may be surprised by the guesses and answers of students. While I think we should ultimately return focus to a study of groups, followed by rings, as is tradition at this point, answering these first few questions and defining this new vector space-like structure with some examples seems appropriate. Eventually we shall return to it anyway. Let R be an arbitrary ring, then we define a left R module as a set M together with a binary operation plus, such that M and plus together form an abelian group. And we have an action of R on M, satisfying for elements in R and elements in M a handful of properties. If R contains a 1, then 1 acts as you would expect. And we should note for the students that if this ring R is a field, then the module is a vector space. Now let's just scan some examples of modules. They are going to be a bit hand-wavy, so I ask for the patience of the viewer or listener. As we just said, any vector space over a field F is trivially an F module. If R is the ring of integers and A is any abelian group, A can be made into a Z module following some kind of procedure, which I am omitting here. If M is a smooth manifold, the set of all real-valued smooth functions C infinity M is a ring, then the set of all smooth vector fields forms a C infinity M module. If R is a ring of differential operators, we can construct these things called D-modules. Again, not going into much detail here, but some of these examples I think are worth mentioning. As to how we would specifically introduce these examples to students is beyond the scope of the current video. However, I think it is important that we even introduce something like a D module to the students, as this is an area of research. By now, students have witnessed on some level groups, rings, fields, modules, and vector spaces. All of these algebraic structures are interesting in their own right. The design of abstract algebra courses and textbooks seems to be around the study of the quintic, in particular, the insolubility of the quintic. I'm not sure I would necessarily change this motivation, rather just shine more light on the path. Everything I have shared here comes from my own lived experience both as a teacher and as a student, and I have not conducted any careful experiments to confirm or support any conclusions I may have already made. I acknowledge many others out there also desire to build a new curriculum with their own approaches and opinions. I hope to encounter more perspectives on pedagogy in mathematics and physics, and I welcome feedback and criticism to my proposals and opinions, ideally in constructive form. Thank you for checking out Math and Physics Academy. I hope you will consider subscribing to this channel or engaging with us on social media at mathphysics.academy. Thank you.